Yaskawa. You are watching the IEC 61131 Basics series. This video is an overview of IEC 61131-3 programming within Yaskawa's MotionWorks IEC software. Hi, I'm Matt Pelletier, and at this point in the video series, you've already been exposed to bits and pieces of IEC 61131-3 programming as you've been following along with me in our programming example. This experience is important as the base of understanding the standard, the programming languages, data types, the software model, and task execution. IEC stands for the International Electrotechnical Commission, and it is a well-recognized world standards organization founded in 1906 with a number of participating countries. So when you're learning IEC 61131-3, you can be confident that you are learning a global standard method of programming PLCs. And here we have a lineup of logos of different manufacturers in the automation industry who do support IEC 61131-3 to some extent. Of course, with Yaskawa being in the center of this discussion. The principal benefit to IEC and programming standards in general is that it allows code to be reused and programming techniques to be shared between different hardware platforms. This allows code development to be implemented quickly using this type of pyramid model, where at the base of the pyramid are the IEC 61131 functions and function blocks. Along with that, for motion is the PLC Open Plus standard, which accompanies IEC 61131, but for motion. And then what you have is the ability for manufacturers to make higher level function blocks that build upon that base, giving a higher level of functionality and bringing the application closer to completion. This leaves only then the highest level, the most specific, application-specific functions and function blocks that make a specific type of machine run a specific application. So because we can reuse much of this code and programming units, it means that programming can be done expediently and that there's control also and testability and the ability to, if you would, certify certain pieces of the code officially to government standards or other standards, specifically the food and drug industry. That often is very important. So more specifically now, what are these standards of IEC 61131? And of course, the most natural and visible standard that will be apparent to the programmer are the 5 standard languages of IEC 61131, which are instruction list, abbreviated IL, structured text, ST, function block diagram, FBD, and ladder diagram, LD. Sequential function chart is considered to be the 5th language, SFC, although it is a bit different. It's more of an organizational tool than it is a programming language. Let's take a moment to examine the code sample, very simple code sample that's given as an introduction to the 5 different languages. And let's compare these 4 here. With instruction list, it's a very low-level machine assembly language type of language where we have load, LD, load, value A, and it with the not of B, and store to value C. In structured text, we would say set the value of C, set the data equal to A, ANDed with the not of B. In function block diagram, you would use the AND operation as a block with inputs on the left, value A and value B inverted or knotted here, output to the value C. And then in ladder diagram language, we have a rung with A in series with the normally closed B, that's the inverted value of B, outputting to the coil C. So these 4 languages accomplish exactly the same thing. And so it comes down to simply choosing and using the language that is most natural for the programmer and most easily accomplishes the programming objective. Now, sequential function chart, you notice, is outside of these 4. We're not trying here to do, in this example, the same code. Sequential function chart, rather than doing this low-level calculation, is more of a sequencing, as you can imagine by the name, a sequencing according to 3 major parts of the sequential function chart language, which is the step, the action, and the transition. Here's another step, action, and transition. And so this is a way to structure and organize in a logical manner the different actions or the different calculations or motions, whatever it has to be done in sequence and in order in a very visual and straightforward manner. So in this idea, you may have fill. Maybe you'd open up the code for fill, and maybe it looks like this in structured text. Maybe the transition is based on inputs, and perhaps it's written in ladder diagram. And maybe this empty is also written in text, or it could be written in instruction list, or in any of the languages can be used within what they call the code worksheets, the code behind the sequential function chart. So usually these 4 languages are familiar to people, and sequential function chart is the least familiar. So let's look a little more specifically here. What is SFC? What is sequential function chart? It is a graphical programming language to describe control sequences in graphical form. It's a tool for top-down analysis and representation of a control sequence, and it is great to show the main states of a program. It's very easy to understand. In this example of a traffic light controller, if I tell you that this is a traffic light example, and you just take a very short amount of time to look at it, you can see, okay, init, the lights are out, there's a area here for true. You can kind of tell top to bottom what's going on. It's a familiar operation. You have a green light, a yellow light, and a red light. And you can see the actions here are to turn the different lights off, wait for them to be done, turn the yellow light on. The yellow light is on for a certain amount of time, looks like 3 seconds. And then the red light turns on, and there's an arrow jumping back to green. So knowing the application, it's very easy to see how this would work. If you are familiar perhaps with ladder diagram or structured text, obviously you could also create this using other languages, but SFC makes it very easy, very visual way to see any sequence. And so this is when you may want to consider using SFC. Is number 1, when there is a definite sequence for the machine to follow. Also, when it is advantageous to think of the machine operation as having different states, such as that traffic light. And then the third one is if you want somebody who's not familiar with your code to be able to work with it. It's very easy to tell with SFC where the problem lies, and then to open up that area of code and look specifically at the area where the problem is or where the operation is currently taking place. Okay, moving on from SFC programming language is another part of the standard of IEC 61131, which we've already seen here as we program, and it's called data types. Every variable and literal value has a data type, and IEC 61131 defines these 20 data types. You can see that each data type has its official name, and there's a number of bits associated with it. There are several different data types that have, for example, 64 bits. So it's not just the size of the data, it is the intended purpose and usage of that data that gives it a data type. And within IEC 61131, you'll hear the term strict data typing or strong data typing. And what this generally means is that any changes of data type will be shown in the code. You will not have in IEC 61131 automatically assuming any conversion of any data types. And while this looks like a long list, in our experience at Yaskawa, there are a few of the data types that seem to appear and are used more often than others. So I've indicated those here. Bool for Boolean, you have bit, 1 or 0, true or false. Integers for negative and positive counting variables. Unsigned integer, where you have just the positive values. The real, and probably more common, the L real, meaning a floating point, a decimal point, is implied and in fact required in those. You have time for the timers, and there's a special format for using the data in time. And then for just standard data, maybe blocks of data coming in from HMIs or from remote I/O, we'll use byte and word. And that's not to say that these other data types are never used at Yaskawa. They certainly are. But if you want to focus on a few of them here, that's the short list. IEC 61131 also describes what they call the software model, which in a sense is more of a hardware operation model. It says that the devices running IEC 61131, in our case the PLC, are referred to as resources, and they exist within a configuration. Maybe you're already thinking of the hardware tab. Let's flip back over real quick so we can relate this to what we've already seen. So here we can see in our project, under physical hardware, we have a configuration, and within that, a resource, within the resource tasks, and within the task list, different tasks with programs running in them. So let's flip back to the presentation. We see these same terms just displayed in a different graphical way here. We have the configuration, the resource is running tasks, the tasks run programs, and then as you know, the programs each run functions and function blocks and have global variables as well as local variables. And so each of these smallest units of execution are called POU, or Program Organization Unit. There's a program organization unit, there's the function POU, and the function block POU. 3 types of program organization unit. This is described and defined by IEC 61131. So now, let's see an example of what a configuration would be in IEC 61131. Here's an example of some type of packaging machine, I believe, with several different controllers, PLCs, operating and controlling the different stages of this machine. And so this assembly of processors running IEC 61131 is considered a configuration. So if we were to take one of these controllers, what do we call that? We call it a resource. And so the resource is the controller. In our case here in our project, it's the simulator. And then that controller is controlling just one part of the larger machine. It may include several servo axes or hundreds even of input and output points, but nonetheless that is considered to be one resource within the configuration, and it's valid to have a configuration which includes only one resource, which is exactly what we have in our project. Every resource or controller, or simulator in our case, must execute the code according to the standards of IEC 61131. And that's what we see inside of the resource folder, is we see the execution, and we see the global variables and the I/O configuration. So these 3 components are defined by IEC 61131. If you go to any other software, any other manufacturer that claims IEC 61131, they will also have a resource folder with tasks, global variables, and I/O configuration. And this is an example here with more than one task. There's a task called start, fast, medium, and slow. And so you can see here that, as it says, multiple tasks run at different system rates. Any of these, what we call cyclic tasks, can run at different rates. And then there are also system tasks that can run based on system events such as power on. And within each task, there are program instances of the program type POUs. It's program type POUs only appear here in the task list. And as you have seen in the previous videos, it's possible to change the order of the program execution. It is top to bottom within each task. And you're able to move, as it says here, move a program instance from one task to another, or even completely remove it so that it doesn't run at all. And finally, I would like to emphasize there are 3 types of POU: the program, the function, and the function block. And only the program POUs run in a task. As it says here, functions and function blocks run in the program. And that's indicated here in this diagram. The program contains the functions and function blocks. That is the functions and function blocks of IEC 61131, such as the counter that we're using, and also any custom functions or function blocks. And later in this training sequence here, there will be a video where we explain how to make a function and how to make your own function block. And when we make those, you will not run them in the task. They will run in one of the POUs as an instruction, just like a counter or any other block that is used in a program. Also, please notice the difference between the folder for logical POUs and the task list. It's common to see that we have a logical POU also in the task list, but that will only be true when the POU is what type? The program type. So the program type of POU can run in the task. Does it have to run in the task? No, it does not. In fact, if you remember back to the programming quick start, we had to create a POU and then add an instance to our task. So it's not required that the logical POU run in the task. It may be a previous version, or maybe for troubleshooting, you don't want it to run at all. And so you can have logical POUs that don't run in the task list. Number one, because maybe they're not a program POU, they're a function or function block. Or number two, they are a program POU, but you just don't want them to run at this particular point in time. Let me just reiterate this then and give a preview. If you wanted to make a function or function block, the first step would be to right-click logical POUs and insert. And here's where you can choose program, function, or function block. So these are the 3 types of POUs. You can see that in your program. And we have created program POUs only, and they're running in our single task. As we move ahead here, we'll make more tasks. We'll end up making more POUs, and we'll end up making our own function and function block. And so with this, I will conclude the IEC 61131-3 programming overview.